In this small segment, we're going to define the trigonometric functions, and we're going to remind in this small segment, we're going to define the trigonometric functions, and we're going to remind you of a property of similar triangles in an effort to do that. You will have had a project that's an introduction to trigonometric functions as well that you may do in class or you may do outside of class, and it's going to help you understand the trig functions, which are ratios, meaning a fraction. So first what I'd like you to do is I'd like to remember that in similar triangles that the ratio of one side to another side in one triangle is the same as the ratio of corresponding sides in the other triangle. You can write that out a variety of ways in all reality. You know, you could say this side is to this side as this side is to this side. So it's one side in a triangle. So I'm going to go ahead and do that. So I could say to you that side AC, the ratio, over BC, those are the two legs. I'm going to pretend this is a right triangle. They do not have to be right triangles. So they just have to be a similar triangle. And the definition of similar triangles is that all the angles in the two triangles are equal to one another. So I've caused this to be a right angle, and I'm telling you that angle B is supposed to equal angle B prime. And angle A is supposed to equal angle A prime. I've attempted to draw those that way. I can't say I did it perfectly. But then what I'm saying is the ratio of this side to this side would be the same as the ratio of this side to this side. Doesn't matter that they're smaller. It just means that if you measured those sides and got a decimal number, that these two decimal numbers would be equivalent. So if this was 4 and this is 2 and this is 2 and this is 1, you'd have 4 is to 2 as 2 is to 1. And those two ratios are equal to one another. Given that information, what we have done in the study of trigonometry is we've noticed that the ratio of two sides in a right triangle can define the size of the angle, and or vice versa. We can take a look at that. So what I want to do is I'm going to try to do an illustration, and I'd like you to pretend or think that I may be drawing a 65-degree angle with the vertex of that angle being at the origin of the rectangular coordinate system, and then I'm going to drop a perpendicular to the x-axis to form a right triangle. Here's what I mean, and I'm attempting to draw a 65-degree angle. And then I'm going to drop a perpendicular, because what I'm getting ready to define is all about right triangles. So you have to have a right angle in your picture. So I have drawn a 65-degree angle, or my version of a 65-degree angle. And would you pretend that I have measured these sides, and that this side right here is 3.45 centimeters, and this side is 7.2 centimeters, and this side is 8 centimeters? Well, somebody else is going to do the very same thing. They're going to draw a 65-degree angle, and I think in an effort to illustrate, I'm going to start over again over here. And I'm going to draw another 65-degree angle, but I'm going to make this one, the right triangle, much smaller. So let's draw this line. This is supposed to be a 65-degree angle. I'm going to drop a perpendicular to the x-axis. And so let's say you did this one and I did this one. And let's say that this side for you measured 1.4 and this side measured 2.8 and this side measured 3.1. So these are actual data points that I have from a class of students that did this with me. Again, remember, these are 65-degree angles. And they are also similar triangles, because they both have a right angle in them. They both have a 65-degree angle in them. So they both have a 25-degree angle in them as well. So similar triangles. So I want to see if the ratios of their corresponding sides might be equal to one another, is what I want to do. So let's go with Pat first. So Pat's x value was 3.45 in this big triangle. So this leg and then my y value, because it's parallel to the y-axis, was 7.2. You could be drawing your own, and I wish you would. And this right here is going to be called my r value, my hypotenuse. So I'm kind of, thinking Pythagorean theorem, but not a's, b's, and c's, but x, y's, and r's. And my r value measured to be an 8. Let's see, yours is the small triangle over here. So your x value measured to be 1.4, your y value was 2.8, and your r value is 3.1. I'm just going to put here that this is the hypotenuse. So we decided to establish a pattern for the trig functions, and that is that the ratio of the side y over r, this side divided by this side, 7.2 for me divided by 8, that ratio would be called the sine of the 65-degree angle. And I have that number to be 0.900 when I divide that on my calculator. X divided by r is called the cosine of an angle. I'm going to spell those out in a bit. My x value was 3.45 divided by my r value of 8. And when you divide those two numbers out, you get 0.431. And finally, my y value, which was 7.2, and my x value, which is 3.4, when you divide those out, you can clearly see you're going to get bigger than 2. And that turned out to be 2.087, I believe. Having a little trouble reading my handwriting. Okay, so you did it with a different triangle, same angles, but different sides. And your y value was 2.8. And your r value was 3.1. And when you divide those numbers out, you got 0.903. Well, geez, that's pretty close to my 0.900. We did pretty good in that we have the same ratio, given that we drew this by hand with just a protractor and a ruler or a scale. Your x value is 1.4. Your r value is 3.1. When you divide those out, you should get 0.452. Look, I got 0.431, pretty close. Finally, I didn't state that this last trig function is called the tangent of an angle, and it's defined as y divided by x. It's always this value divided by this value. So your y value is 2.8, and your x value is 1.4, and when you divide those out, you get 2. I like to carry the values of my trig functions to the thousands place, so I'm writing that as 2.000. Well, lo and behold, when we pull up a calculator and we check, let me see if my calculator's in the degree mode. So I'm going to run that by you one more time. So you hit your mode key. So I hit this red mode key, and I arrowed down 2 and then to the right 1 and hit enter with my cursor on degree. So it would be in the degree mode versus the radian mode. And we said that this was a 65-degree angle. Do you see the sine, cosine, and tangent button? I'm going to quit to get out of this mode. So second, quit whenever you don't want to be where you are. And when I check and see what the sine of 65 degrees actually is, I find out that it's 0.906. Well, look, you were closer. You had a 0.903. I had 0.900. Remember, we sketched these by hand. I attempted to sketch these by hand. When I check the cosine of 65 degrees, that turns out to be 0.4226. Look at our 0.452, our 0.431. We're very close. And then the tangent of 65 degrees should turn out to be a little bit bigger than 2. So sure enough, it does. So what this means now is if I know the size of an angle, for example, and I'm just going to do a sketch over here. If I know that I have a 65-degree angle right here, and I can measure a distance right here, for example, let's say that I'm looking up to the top of a tower and I'm standing on the ground looking at a 65-degree angle up to the top of that tower, and I'm 55 feet away. I can find the height up to the top of that tower, because for this 65-degree angle in this scenario here is I want to know the y value and I have the x value. and I know I have a 65-degree angle. So I would use tangent. I would say that the tangent of a 65-degree angle, which I can look up on my calculator, is equal to the ratio, that y side divided by that x side. And to solve this for the height, I'd multiply both sides by 55. In other words, I'd bring that 55 over here, and I would take, remember, I know that the tangent of 65 degrees is this, and then I could multiply that by the number 55, and I know now know that the height of that building was 117 feet. So that's where I'm going to use this. Again, oh, I'm sorry, 118 feet is what that was. So if I know an angle and I want to find a side that's inaccessible and I know another side, I'm ultimately going to be getting to that point where there's three pieces of information in these trig functions. One is the size of the angle, and then the two numbers that represent the fraction. So I'm going to explore some more in our next segment. You should as well be working on that intro to trig functions.